Pluto, the mysterious dwarf planet lurking at the icy edge of our solar system, continues to fascinate scientists, astronomers, and curious minds across the globe. Though it was reclassified from full planetary status in 2006, Pluto remains a symbol of cosmic wonder and scientific intrigue. It's not just an icy ball drifting in space. It's a key to understanding the deeper forces that govern celestial motion and planetary dynamics. Nestled beyond Neptune in the vast Kuiper belt, Pluto travels a lonely, frozen path. But recent discussions among astrophysicists have sparked questions that go far beyond classification. What if Pluto and Neptune could collide? Could the gravitational harmony that governs their movements break down? Is chaos hiding beneath the seeming balance of space? While it might sound like a wild science fiction scenario, the idea of a Pluto-Neptune collision prompted researchers to examine the complex ballet of orbital motion more closely. Experts like Neil deGrasse Tyson and Michio Kaku have weighed in, not to stir panic, but to reveal the stunning dance of gravity that makes such an event virtually impossible, yet scientifically captivating. Pluto's orbit is not ordinary. Unlike the smooth, nearly circular paths of Earth or Venus, Pluto's journey is eccentric, stretched, and tilted. Its elliptical orbit takes it on a 248-year-long trip around the Sun. So long, in fact, that Pluto still hasn't completed a single full orbit since its discovery in 1930. Even more unusual is the 17-degree tilt of its orbit. Most planets follow the ecliptic plane, a flat disc-like path around the Sun, but Pluto moves at a steep angle, carving a unique trail through space. At certain points in its journey, Pluto's orbit even crosses Neptune's path. For about 20 years in every 248-year cycle, Pluto is actually closer to the Sun than Neptune. That sounds like a disaster waiting to happen, but the universe has other plans. Despite the overlap, Pluto and Neptune never collide. Why? The answer lies in a phenomenon called orbital resonance. For every 3 orbits Neptune completes, Pluto completes exactly 2. This perfect 3:2 resonance ensures that the two worlds are never in the same place at the same time. When Pluto crosses Neptune's orbital path, Neptune is always on the opposite side of the Sun. It's a cosmic choreography, a gravitational dance, timed with exquisite precision. It's not luck. It's the laws of gravity in motion. Scientists call this resonance a gravitational buffer. It's a vibrational effect that keeps Pluto at least 90 degrees away from Neptune in orbital longitude when it comes close to danger. Imagine a perfectly synchronized waltz, where 2 dancers move across a vast ballroom, never stepping on each other's toes, despite sharing the same floor. Still, Pluto's orbit isn't entirely stable. Simulations from the late 1980s revealed something even more fascinating. Pluto's orbit is chaotic. That doesn't mean it will crash into Neptune or spiral into the Sun, but it means that small changes, tiny shifts in speed or position, can have massive consequences over millions of years. The math becomes unpredictable. This kind of chaos makes long-term predictions difficult, yet somehow Pluto remains stable over billions of years. This suggests that even in chaos, there is hidden order, a mystery scientists are still trying to unravel. Neil deGrasse Tyson, who played a major role in Pluto's reclassification, emphasizes that this change wasn't meant as a slight, but as a step towards scientific clarity. He views Pluto not as a demoted world, but as an important laboratory in space. Its strange orbit, its position in the Kuiper belt, and its gravitational interactions make it a powerful teaching tool for understanding the mechanics of our solar system. Tyson once said that by observing Pluto's motion, we learn more about how balance is maintained in the apparent chaos of the cosmos. Michio Kaku, a theoretical physicist and one of the pioneers of string theory, sees Pluto's orbit as a bridge between gravity and quantum physics. He suggests that if Pluto and Neptune were ever to collide, a nearly impossible but theoretically rich scenario, the resulting impact would generate gravitational waves. These waves could offer insights into the structure of spacetime and the universe's origins. According to Kaku, events like these mirror the extreme conditions that existed just after the Big Bang. Studying them could bring us closer to one of physics' greatest goals, unifying general relativity and quantum mechanics. Even if a collision is unlikely, Contemplating such an event helps researchers model planetary systems. Supercomputers now simulate millions of years of orbital motion, showing how planets interact, shift, and affect each other. The gravitational influence of giant planets like Jupiter and Saturn plays a crucial role in shaping the paths of smaller objects like Pluto. Without the stabilizing effects of these gas giants, the solar system could fall into disarray. Planets flung into deep space, orbits disrupted, chaos unleashed. The motion of Pluto reflects this balance between chaos and order. And it's not unique. Other planetary systems exhibit similar dynamics. The TRAPPIST-1 system, with its 7 Earth-like exoplanets, follows a resonance chain so precise that even a slight disturbance could lead to system-wide collapse. These planets orbit in lockstep, but they're vulnerable. One planetary wobble could send the entire system into disarray. This leads us to the concept of rogue planets, worlds that have been ejected from their systems after gravitational turmoil. Some scientists believe that these free-floating planets may outnumber stars in our galaxy. If one ever wandered into our solar system, it could shift orbits and wreak havoc, even disturbing Pluto's delicate path. Fortunately, space is vast and such encounters are rare. Still, studying Pluto helps us prepare for these possibilities. It teaches us how gravitational forces interact over time, how systems adapt, and how we might protect our own planet in the far future. These studies also tie into the famous three-body problem in physics, a challenge that has baffled scientists for centuries. It explores how 3 gravitational bodies influence one another and how even small changes can create vast unpredictability. With today's technology, scientists use simulations to navigate these chaotic systems, helping them forecast orbital motion, identify habitable zones, and even track potential threats. Pluto's orbit, once seen as a curiosity, is now a key to unlocking deeper truths. It may even help us locate exoplanets with similar odd behaviors, like Sedna or the mysterious Planet 9. As our computing power grows, our understanding of these complex systems improves. Supercomputers can now model billions of years of movement, uncovering patterns we never saw before. These aren't just interesting, they're essential. They help us understand how the early universe worked, how planets formed, and how solar systems like ours hold together. Neil deGrasse Tyson famously said, "The universe is under no obligation to make sense to you, and Pluto is the perfect example. Its motion may seem chaotic, but it hides a stability that teaches us about the very fabric of space." Michio Kaku echoes this sentiment, saying that every anomaly in space is a clue to something deeper, a secret waiting to be discovered. From tilted orbits to gravitational dances, Pluto is more than just a dwarf planet. It is a cosmic laboratory, a gateway to understanding time, motion, and the balance of the universe itself. Even at the outer edges of our solar system, Pluto reminds us that the cosmos is alive with mystery. And the more we study it, the more we uncover, not just about Pluto, but about the countless planets, systems, and galaxies beyond. With every orbital calculation and simulation, we inch closer to understanding the grand truth of our universe. So keep watching, keep questioning, and remember, sometimes the smallest worlds hold the biggest answers.